Summarizing quantitative data, histograms. We will discuss two aspects of summarizing quantitative data, which you may recall are numerical measures with units in a context. For graphs, we will discuss histograms and box plots. This video will focus on histograms. Box plots will be discussed in a separate video. We will also discuss numerical summaries in other videos. 1. Measures of center or typical values. We will focus on the mean and the median. 2. Measures of spread or variability. How spread out are values. The bold terms, interquartile range and standard deviation, are the more important ones, which will recur in other material. Three, other measures. These represent other location values. The minimum, Q1, or the first quartile, Q3, third quartile, and maximum. The histogram is perhaps the most common graph used to display quantitative data. A histogram is created by dividing the set of possible or observed values in a data set into sections called bins. Each bin represents the edges of rectangles, which will be equal width, with heights determined by counting how many values in the data set fall into the bin. When the data are discrete, such as counting number of siblings, then the histogram will often use each unique value as a bin, where rectangles are drawn with bases extending halfway between the possible values. Since data may consist of only children, so 0 siblings, 1 sibling, 2 siblings, etc., we could create bins where 0, 1, 2, and so on are at the center of our rectangles. So the first bin would go from -1/2 to +1/2. The second bin would go from 1/2 to 1.5, and so on. When data have too many values to let each unique value be its own category, such as weights of automobiles, we create bins to cover a range of values. This is typically labeled as continuous data in these cases. For example, if we recorded the weights of vehicles, we might define bin 1 as weights of automobiles from 2,500 to 3,000 pounds. Bin 2 as weights of automobiles from 3,000 to 3,500 pounds, etc. We actually decide whether to include the left number or the right number in the leftmost bin. For example, we have to decide whether 3,000 pounds should be counted in bin 1 or in bin 2. The good news, we'll let StatCrunch do all this for us. Consider the weights in pounds for a random sample of 80 automobiles. See the file autoweights.xls in the StatCrunch group. Load the data file, click the file in the group, and it will load into StatCrunch. Then the commands used to obtain the histogram are graph histogram, left click on the weight variable. Under bins, where it says start at, type in 2500, width, type in 500, enter an appropriate title such as weights for 80 automobiles, and click compute. I'm going to go over to the StatCrunch group. Here's our auto weights data file, so if I left click, it loads into StatCrunch. And then here are the commands. Left click on weight. Where it says bin start at, type in 2500. Where it says width, type in 500. If you want the values above the bar, you can click the box, enter a title, and then click Compute. Remember to copy the graph and place it in a Word document. You would use Options Copy in the top left corner of the window that pops up, and then Copy Image. And then in your word processor, you can use Control-Alt-V and paste it as a device-independent bitmap. So the histogram from StatCrunch is here. What characteristics are important to tell about the weights of automobiles? The smallest value, or the lightest automobile. Note, from the graph itself, you can only give the range of values it covers. Now we know the width is 500, so this would be 2,500 to 3,000. The largest value, or heaviest automobile. Note again, you can only give the bin's range in this case. The approximate shape. Symmetric, skewed left, skewed right, uniform, none that we define. We'll talk about these a little later. The most commonly occurring value or values. Identify the locations of the modes or the tallest bars. And are there any unusual values called outliers? An outlier, or several outliers, would stand far away from the other values in the histogram. They would be obvious. Using only this histogram, what would our description look like for the auto weight data? The lightest automobile weighed between 2,500 and 3,000 pounds, the leftmost bar. While the heaviest automobile weighed between 6,000 and 6,500 pounds. The most commonly occurring automobile weight, where the tallest bar is located, is between 3,500 and 4,000 pounds. The shape of the histogram is skewed to the right. Note there are two rectangles to the left of what I call the most common. The most common is this tall bar. There's two rectangles to the left. How many are to the right? There are 5 rectangles to the right. So as such, the data stretches much more to the right than to the left. So we call it skewed to the right. There were no automobiles with weights which would be considered an outlier. None of the values have a rectangle which has a lot of white space or non-observed values between it and the rest of the data. So let's put this in more of a paragraph format. So this is what our description might look like in this case. A graph does give a snapshot of the information, but since we have the data, we can also look at numerical characteristics. For example, we can actually go back and get the actual lightest and heaviest weights and report those since we have the data file. Give as much detail as you can for an exercise. If all you have available is the graph, the histogram, you can only give the range in which the lightest car or the heaviest car falls. If you have the actual weights, you would report it instead. Notice shapes of a histogram can be different. What is meant for each shape? All the examples use the histogram sim.xlsx data file. You can recreate these graphs if you set the starting value and the width for the bins. First, consider the most common value, assuming that you have a mound-shaped histogram where there's a tall bar or a few tall bars. From the most common value or values that you indicate, count how many rectangle regions exist to the minimum or to the left side and to the maximum or the right side. If there are two or more additional bars on one side than the other, call the data skewed that direction. If there are the same number or just one more additional bar, call this approximately symmetric. If the rectangles tend to be similar in height without any mound shape, you can call this uniform. If a histogram does not match any of these general patterns, just say the shape is not one we defined. Notice below, in this left graph, the three tall bars are between 2 and 4. There are 2 bars to the left to get to the minimum value of 0, and there are 6 bars to the right to get to the maximum value at 10. Since 6 is 4 more than 2, we would call this shape skewed to the right. It is also called positively skewed in some terminology. In the right graph, the tall bars are between 18 and 20, with 1 bar to the right, but 5 bars to the left. Hence, we would call this shape skewed to the left, or negatively skewed. In this left graph below, the tallest bars cover values from 90 to 110. There are 3 bars to the left of these 2 most common, and 2 bars to the right. In this case, 3 versus 2 only differs by 1, so I would call this histogram approximately symmetric in shape. In the right graph, notice the rectangles are nearly the same height. This shape is called uniform. Last, this is a histogram with an extreme outlier. This is an unusually low value in the 20 to 30 region, very far separated from the other data. This concludes the video on histograms.